fellow assistant for the academic year, and then I'll be back at the University of Maryland. I'm a geography professor.
Hi, I'm Heather Randall. I'm a postdoc. I'm a sociologist and I study the health and social effects of climate change.
Hi, I'm Chris Field. I'm a postdoc here. I study cultural ecology and conservation.
I'm Bianca Lopez, also a postdoc, and I'm an ecologist and I study urban biodiversity and green spaces.
Hi, I'm Danny Weissman. I'm a PhD student and a research assistant here, and I study coastal agriculture and soil chemistry.
Hi, I'm Hannah, and I'm a master's student at Maryland, and I study wetland carbon and soils. Hi, I'm Carrie Ritz. I'm the associate director for research.
Billy Hall. I study how structural racism shapes ecological landscapes in cities.
Cool.
My name is Alec Armstrong. I'm a PhD student. I study the role of organic matter in stream ecosystems.
I'm also Green. I'm an assistant on the data science and communications teams.
I'm also a Percival Canberra. I'm a filmmaker and the multimedia specialist here.
I'm Hillary Kelvick, we met, and I'm a PhD student working on the public health implications of non-traditional irrigation water sources.
Hi, I'm Chris Jesus, postdoc here. I work on biodiversity and climate change and biodiversity and adaptation.
Hi, I'm Cindy Way. I'm the associate director of education.
Hi, I'm Philip Stanichenko. I'm a postdoc here and I study food webs.
Hi, I'm Christine Mayetta. I'm interested in soil microbial ecology and methane emissions from wetlands, and here at Sasenka helping with this.
Hi, I'm Kelly Hundul. I'm part of the data science team here, and I'm a PhD student at Maryland studying methane emissions from wetlands.
I'm Dexter Lock. I'm a postdoc. Thanks for chatting with me earlier.
Sure.
Cities, trees, and people.
Hi, I'm Kiana. I'm also a postdoc here and I study urban green.
I'm Dean Hardy. I'm a geographer. I'm also a assistant postdoc, and I study climate change, environmental justice, and water ecosystems.
Cool. I think that's everyone.
Yeah. Okay. So, thanks for coming, Ashlynn.
Sure.
Ashlynn she got her her undergrad in chemical engineering.
I did.
at the University of Missouri. And then she got 2 masters, one in environmental and water resources engineering and another in public affairs at UT Austin. And then she went on to get her PhD in civil engineering at UT Austin. We won't hold that against you.
I figured you would hold the Mizzou part against me from Arkansas.
This year. And she did 2 years at an engineering firm, Burns & McDonnell. And then she also did a year with the Policy Research and Congressional Research Service. She's involved in a lot of service, and of note, in 2015, received the Girl Scouts Woman of Distinction Award for Illinois. And turn it over to you.
Great. Well, thanks for having me. And I guess I should say how Nate and I met, which was on Twitter. So never underestimate the power of social media, that you might in fact find some very interesting folks on Twitter. So today I'm impressed with all of your breadth of areas of research. This is super impressive, and each one of you must have really practiced how you pitch your work, because you're very snappy and to the point. This is sincerely impressive. So, I mean, among the things that my group and I do include things like green infrastructure and urban stormwater and things along those lines. I won't be talking about those today, but I'm happy to talk more about it and some of the biodiversity implications of power plants in particular are among the things that my group studies. But today I thought I'd talk to you about energy and water sustainability in cities, and a way to kind of visualize what's going on with the energy water nexus is this figure. So a lot of times this gets kind of thrown around in lingo, the energy water nexus. It's a fun thing, but really how we break that down and kind of tease it apart is we use energy for water, we use water for energy. And so mostly what I'll be focusing on today is this top half here, of energy for water. So there's energy embedded in every single part of the water sector. If you think about your morning routine, for example, you're going to come up with a lot of energy embedded water uses. Getting drinking water to your house requires energy for treating it and energy for pumping it. We've carried water. We know that water's heavy, so moving water around takes a lot of energy. And then once we get to homes, a lot of times we as consumers add more energy to water for, say, that super hot shower. Water heating, just raising the temperature of water, takes a lot of energy. And then the water that comes off of that shower and our toilets and our sinks and all the other stuff goes to a wastewater treatment plant where we add even more energy to it. And in the event that we want to reuse that water for something, water reuse incurs more energy. So if you imagine this water molecule kind of going through the urban water system, it's picking up embedded energy along the way. And so what my student Chris Cheney and I set out to do is to start to put numbers to that. So we have a whole bunch of estimates in literature. A lot of times those are extrapolations that are based on 1 or 2 or 3 or 4 or 5 data points extrapolated for the entire United States. And many of you are studying things like biodiversity. You know that one location is not identical to another location across the country. Or you could have one location that is 20 miles away from another location and they're nothing alike. So regional differences sometimes can be pretty vast and nationwide differences can be pretty vast. So we tried to start putting numbers to this idea. We won't really touch on the bottom half here, but the main takeaways are that anything that is an energy source requires water in order to get it in that usable form. So having electricity to run the projector and the computer and the lights and all of that requires water for cooling power plants. Use of primary fuels like oil and natural gas require water in extracting and refining those fuels. This is true of conventional hydrocarbons or of unconventional hydrocarbons. So a lot of times people think of things like hydraulic fracturing, which is very much a water for energy example. But even in conventional oil and gas wells, we still have water associated with that. And things like hydropower are a very visual way to convert between water and energy. So this is the energy water nexus. What I thought I'd do today is talk about the city from 2 different scales. So we could think about the city from the top down. Think about this city as an organism. This is a concept called urban metabolism, where you just kind of lump all the things that define the city into one entity. Or we could think about the city from the bottom up as a collection of buildings. So we'll start this morning with the city as an organism and start at the city scale. So as my student Chris and I were looking at this question of the urban water sector, we decided to do a data-driven analysis, and we asked ourselves what current data are available. And spoiler alert, there aren't many. And they're often of kind of questionable quality or of a questionable way to compare between those data sources. So our classic source for water data is the United States Geological Survey and their National Water Census. Have any of you used this data source? It's a county scale data source that only represents water withdrawals that happen inside that county, and it's estimated every 5 years. So a city like Los Angeles wouldn't show up on the National Water Census as requiring a whole lot of water for the municipal sector because not a lot of Los Angeles's water comes from that county. A lot of it is coming from outside the county. So we're not getting that inter-county movement of water in the National Water Census. It's also only focusing on withdrawal, so it's estimating what's coming out of a river or an aquifer, but not necessarily what is consumed in evaporation. We haven't actually measured those since 1995. So the USGS data can be the best thing we've got, but still have some flaws. There's a nonprofit organization called Circle of Blue that does some interesting work with water prices and the price of drinking water in different US cities. These are usually estimated every year, but it's only focusing on price, not necessarily quantity. And lastly, the American Water Works Association on a national level has this publication that they call Benchmarking Performance Indicators for Water and Wastewater Utilities. It has data for water and wastewater utilities that are members of the AWWA, Those are usually public utilities, but could be private utilities. And what the AWWA does is charge you money for this report, and then they aggregate everything to different geographic regions in an effort to not reveal information about a specific city. And one of the things that we found in our analysis is that geographic clumping together doesn't really make a whole lot of sense. There's some state level data in California and in Texas, but generally speaking, there's no good way to find how much water is treated by a water or wastewater utility and how much energy they might use for those processes. There is a parallel for this on the energy side of things. So on the water for energy side, we have a database in the U.S. Energy Information Administration, which is part of the Department of Energy, on how much water is withdrawn and consumed for each individual power plant above a certain capacity threshold in the United States on a monthly basis. So there is a form or a model for this, but we just plain don't have it on the water side of things. So when you don't have data, what do? You collect it, right? Well, the way you collect data from water and wastewater utilities is to submit open records requests or Freedom of Information Act requests. So my student Chris, over the course of 2 years, sent a lot of different forms of communication to all of the cities that you see here represented with blue dots. And what he was trying to do was get a geographic distribution of cities and to get something that represented each individual US state. So we started with targeting cities of populations over 100,000, except in the case of states that didn't have a city over 100,000. So we recognize that city means different things to different folks. My hometown has 5,000 people, so 100,000 people is a huge city in my perspective. For those of you that might be from New York, that seems laughable. That was our criteria. And one of the things that, so Chris and I wrote an editorial on this process of collecting data. He could probably come here and talk for an hour about some of the hilarious things that have happened to him in an effort to try and get data, including one utility that wanted to charge him $500, one utility that charged him 41 cents and he had to write a check for that, one utility that refused to release information because of I think the direct quote was the potential to reveal potential vulnerabilities in our system, and so on and so forth. So he sent letters, he made phone calls, he sent emails, and he contacted these utilities on Twitter. Any guesses as to the most effective ways to communicate? Twitter and mail. Like the two opposite ends of the spectrum. It's really easy to ignore emails, it's really easy to ignore voicemails, but papers get pushed around a lot, and you eventually find the person. And Twitter's very, very public. So he got the best response rates on the opposite ends of the spectrum. And in putting numbers to that, how do cities respond? These 4 pie charts give you some perspective. So the top row is the temporal flow resolution, and the bottom row is temporal energy resolution. And the dark blues are daily, going down to monthly, and then annual, and then gray represents no response. We sent these to public utilities who are actually required by law to respond. So by law, the gray part actually shouldn't exist there. But the truth is a lot of drinking water utilities didn't respond. More wastewater utilities responded on the far right column than drinking water utilities on the left column. And we got better resolution, temporal resolution of data when it came to flow than with energy. And this was pretty obvious when we started digging through the data that energy is less important of a concern for urban water and wastewater utilities than things like flow. Because there were times that Chris requested how much energy was consumed, and he got photocopies of the monthly utility bill sent over from the accounting department. So what that reveals to us is that there's a disconnect between who pays the electricity bill and who's making the decisions when it comes to the sustainability of the system and providing service for drinking water and wastewater. So this was an adventure in collecting data, and our goal in all of this was to start to understand the urban water cycle. So if we think about what happens in the urban water cycle, we have water that comes in from water supply. We add energy to it, so the red flows are energy, in order to get raw water to a source as drinking water. Some of that water leaks. We call that non-revenue water. In the industry, it's called non-revenue water because it's either physical losses like leaks or water main breaks, or it could be apparent losses like a meter inaccuracy or a billing error. All of that is lumped together in this term non-revenue water, which has some energy embedded in it because we put energy here to treat the drinking water. So that goes to our customers, and then we have rainfall that comes in and becomes stormwater runoff and wastewater that comes out of here. I'm sorry, it's hard to see because we thought we were funny and we made it brown because it was wastewater. Brown on black is not quite as good of a contrast. There's energy embedded in that. In some cities, these two flows might be combined in a combined sewer. And in some cities, we might recycle some of this treated wastewater effluent back to either the water supply or in a non-potable application in the built environment. So there's lots of flows of water in the urban environment. There's lots of flows of energy associated with those. So we collected all these data and we started to put numbers to them, and this is what we got. This is drinking water. And in this map, these are cities that responded to our request. The size of the circle represents the per capita drinking water consumption in liters per person per day. So larger circles have larger per person water consumption. And the color of the circle represents the embedded energy. And we go from cooler colors to warmer colors, with warmer colors representing more embedded energy. Some of them that are gray either didn't report energy, or in the case of Kansas City, I grew up near Kansas City, so I can kind of pick on them. They gave us a number. It was like 2 orders of magnitude different from everyone else. Chris got back in touch with them and said, hey, are you sure? Here's what we get, and here's the average of everyone else. And they said, nope, that's right. So we're not so sure what's happening here in Kansas City. But what we see, just from looking at this, and we did some spatial statistics on it, is that there's really no trends. We couldn't clearly group drinking water utilities into, say, the northeast, southeast, southwest, northwest, because they're very different. Every urban water utility is unique, and while the AWWA will say everything here in the southeast is about the same, our results show that's not really the case. So when we try and group these into spatial clusters, we actually get nothing statistically significant. When we look at the wastewater side of things, there's a little bit clearer of a picture. So same story here, where the size of the circle is proportional to the per capita wastewater production. And the color of the circle is the embedded energy. We do get some clustering, geographic clustering, that happens here. And a lot of this has to do with combined sewers. So these are areas in the country that have combined sewers. So what we're capturing in this kind of band area is the collection of both sanitary waste and stormwater together in the pipes going to the wastewater treatment plant. But that's not absolutely true, because there are other areas that have combined sewers as well. So we can generally clump them together, but overall it's hard to do this kind of geographic regionalization when it comes to urban water and wastewater systems. So that's on the spatial scale. We also looked at a temporal scale, and these are 6 example cities. The cities on the top, Anchorage, Boston, and Colorado Springs, in addition to this one down here in the corner of Salt Lake City, are in mostly colder climates versus Dallas and Oklahoma City here in the bottom left. What we notice is, if we look at the solid line in each one of these figures, drinking water consumption is typically higher in the summer than it is in the winter, which we probably could have guessed before going into this. A lot of you talked about doing things with green infrastructure and outdoor landscapes. That's exactly what's happening in this drinking water consumption being higher in the summertime than in the wintertime, is outdoor irrigation. And we can see that without having to look at every single meter in the city. We look at what comes out of the drinking water treatment plant. The interesting thing, however, are these dashed lines. So these dashed lines represent the embedded energy in this water. So this is normalized to the amount of water that's being treated. And in colder climates, we have higher energy embedded in water in the wintertime than in the summertime. And that's distinctly different from places like Dallas and Oklahoma City that have a similar trend in their embedded energy on a monthly basis. And we discovered this has to do with use not only of electricity for treatment and distribution, but also of other primary fuels. In colder climates, there's a non-negligible amount of natural gas and fuel oil that is consumed for space heating and for water heating at these utilities, such that we have higher embedded energy in the wintertime than we do in the summertime. And previous studies of this had just assumed that we're only ever talking about electricity, and that's all we really need to pay attention to. In the process of collecting these data, we asked for all energy, and we got a lot of information about natural gas and fuel oil that turns out is quite significant, especially in colder climates in the wintertime. So this was an interesting thing that we learned. We also, through the joy that is Twitter, collected a lot of non-revenue water data. And so these circles are just representing the cities that we heard from, and the color corresponds to non-revenue water in a percent. And it ranges from 4% to 45%. A lot of cities either estimate this roughly based on the difference between drinking water and wastewater flows. It's really hard to pinpoint what is non-revenue water, and it's a whole lot of estimation. For those of you that aren't familiar with urban water, 4% is really low. The American Water Works Association recommends 5% as a goal. So 4% is really great. Although it might seem horrible that 4 of every 100 gallons is not making it to a customer, that's a lot better than roughly half of the gallons not making it to a customer. So when we average this over the entire United States, we see that about just shy of 16% of drinking water is non-revenue water. So about 1 of every 6 gallons of water treated never makes it to a customer. And we assessed how much energy was embedded in this drinking water, and we see that the embedded energy is about enough for 300,000 US homes, which is a lot. Going back to what defines a city, we could power a pretty good sized city for an entire year just by fixing the non-revenue water problem. It's not easy to fix because all pipes leak, and they will leak over their lifetime, but they're not designed from a hydraulic engineering perspective. We don't design pipes to leak at 45%. So there's a lot of headway that we can make with upgrading our infrastructure, which seems to be something that folks are talking about in Washington a lot these days. So to kind of sum this up, before we go down to the individual building scale, what we learned at the city scale is that water and wastewater utility data are really hard to come by, but we can get some of them. And we make a case that these should be reported in a centralized, publicly available database. We find that both primary and secondary energy sources are important when it comes to assessing embedded energy, primary being things like natural gas and fuel oil, secondary being things like electricity, a fuel that is an energy source that is generated from a primary fuel. Non-revenue water is significant, and it's about the same amount of electricity as 300,000 US homes. And really what we find, kind of zooming out big picture, is that the sustainability of a city goes beyond the consideration of one specific resource. So we came into this wanting to study the urban water sector, but truth is, water efficiency is a good approach to energy efficiency, which a lot of cities have goals to meet different energy efficiency standards. Water is one way to get there. All right, let's go to the residential scale, because really cities can just be collections of buildings. Buildings don't use water and energy. Humans in buildings use water and energy. So how do they do that? So we looked at the residential environment because it's kind of an interesting microcosm of the energy-water nexus, of this connection between water and energy. And the pie chart on the left-hand side is residential energy consumption, and these are estimated by the DOE about every 5 years based on the Residential Energy Consumption Survey. So these numbers are from 2009. There will be newer numbers coming out if they're not already. They go through a QA/QC process, so there's a bit of a delay in how often we have numbers. But if we look at total per household, the lion's share goes to appliances and to space heating. Space conditioning has always been the lion's share of the residential energy consumption. But if you look backwards in time at these values, there's a reason this 29% is called other, because when it first started, it really was an other category. It was tiny. So I don't know how old you all are, but when I was a kid, we didn't have that many things that plugged in. And my guess is you were in a similar position. You maybe had one TV in your house, and we didn't get a microwave until I was 6 or 7. So the things we had that plugged in were like TV. Ooh, that one time we got a VCR, which was cool, and a toaster and a blender, and like alarm clocks and stuff. Fast forward 35 years, we got a lot of stuff that we plug in, right? This other category has really grown such that we'd love to be able to break it down, but this is all the stuff that you plug in, which can be large consumers of energy. One of my undergraduates did a study on things like cable boxes. They're in the industry, they're called set-top boxes. Their ultra-low power state, their sleep mode, still uses 90% of their full power electricity. So there's a lot of stuff that you probably have plugged in your house right now that's just chewing up electricity along the way. And that's what goes into this other category. But space heating, water heating, space conditioning, if we lump in air conditioning, is a lot of this. On the water side of things, this pie chart makes it look like we have a pretty good handle on this because these values are from 2016, but this is only the second time we've estimated this, and the time before that it was from 1999. So we don't have a really good handle on how people use water in their homes, and this is a nationwide average. So nationwide, a lot of us are growing a beautiful crop of lawns with our drinking water. But this can be 80% if we say lived in Phoenix, and it could be as low as, say, 15 to 20% if we live in a dense urban area like New York or Boston, where there really aren't lawns to speak of. So this particular part of the pie can vary widely. What we do see is that inside the home is pretty consistent, and we've kind of got a split between things like showers, clothes washers, and toilets as the large items and faucets, and the amount of water that we actually use for drinking is quite small. Yet the way we've plumbed our homes in the United States per plumbing code is that everything here is drinking quality water. So it's kind of a snapshot of the residential built environment. And what my students and I did is to compare the direct and indirect consumption of water and energy in the home. And the clothes washer is probably the most complex appliance we could think about as to how this connection plays out. So when we use a clothes washer, it's plugged in to the wall. So we have some amount of electricity that is just to operate this machine. And we have drinking water that goes into it to wash the clothes. And we might have heated that water if you wash your clothes in warm or hot. So there might be some energy associated with water heating that goes into this machine. Or if you have some fancy pants washing machine, it might do onboard water heating. And there's wastewater that comes out of it. So these are direct consumption of resources that happen inside this appliance. But there are indirect consumptions of resources associated with each one of these direct things. So if we start at the bottom, the electricity that goes into the washing machine has water consumption associated with cooling the power plant that it came from. The drinking water and wastewater has energy associated with treating that water as drinking water or wastewater. And there's water associated with natural gas or electricity that's used to heat the water in a water heater. So there's both direct and indirect consumption of resources here in each one of these individual appliances. The clothes washer and the dishwasher are kind of the ones that represent the most complex thing. But if we had a similar picture for something like a faucet, a toilet is actually about as simple as it gets because they only run on cold water if your house is plumbed correctly. Although my parents' first house had one of their toilets plumbed to hot water on accident. So there's always strange things that can happen in these old houses. But if we had the same picture for a toilet, we'd have drinking water going in, wastewater coming out, energy embedded in those. So this is kind of the most complex example we could talk about. So with this in mind, the question we answered then is, what upgrades make the most sense from a water and an energy perspective? We could get a new clothes washer, replace that top-loading, big, kajunk type washer that uses a whole bunch of water and a whole bunch of electricity with one of these really cool things that you see on the Black Friday ads, the front loader super high efficiency. What's that cost, and how much do we actually save? Those are the questions we were trying to answer. And we do that in a very economics approach with what's called an abatement curve, a cost abatement curve. And these are super information dense diagrams. Have you all seen these before, a cost abatement curve? The traditional approach is what's called a Mckenzie curve for carbon. So this idea comes from economics, and what we have is it's essentially a bar chart, and each one of these bars represents an individual appliance or fixture inside the home. This is for energy, so there's a lot of things in the home that use energy. And the upgrade to an Energy Star or a WaterSense fixture. WaterSense is the water equivalent of Energy Star from the US EPA. And the width of these bars represents the amount of energy that we could save annually. And the height of the bars represents the abatement cost. So a negative abatement cost is something that saves you money in the long run. There's an upfront investment in the new washing machine, but you save money over the life of the appliance. A positive abatement cost is an investment that makes no economic sense because you won't save the money that you invest. Does that kind of make sense? So what a cost abatement curve does is ranks these from low to high cost, such that if we say wanted to save 3,000 kilowatt hours per year, the most economically efficient thing to do would be to read this here and invest in everything from here and to the left, which would be things like low flow toilets, CFL lighting, kitchen faucets. There's that cable box. You can get an Energy Star cable box. They don't actually save much energy because they're already consuming so much energy. These big ones are windows, and a clothes dryer is also large. So we would invest in these things and not invest in things like an air conditioner or a new wireless router or an upright freezer and these other furnace type items on this side. What we find is that there's significant savings when we consider both direct and indirect consumption of energy. The toilet itself is not consuming energy, we don't plug it in, but because of the drinking water and wastewater in it, there is energy savings associated with it, though it's quite small. We find that we can save a lot of energy and that a lot of it is cost negative, meaning we would save money over the long run in these investments. This is the picture for energy. The picture for water is a lot simpler because we have a lot fewer options for how we use water in the home than how we use energy. And the key takeaway on the water side is that there's only one appliance that is cost positive, and that's a dishwasher. And it doesn't save that much water anyway. Everything else is a cost negative thing. So one of my friends at the University of Illinois is an environmental economics professor, and she looks at stuff like this and she totally geeks out over it, and she kind of shakes her hands because these are dollars on the table. From an economist perspective, this is money on the table that consumers are not taking by investing in things like an Energy Star clothes washer or an Energy Star water heater, these other things that could save money and resources over time. But what do we know as consumers? That upfront investment is expensive, right? Like there's a reason you're probably going to wait for the Black Friday sale, or you'll wait until your municipality might offer you a rebate or an incentive of some kind. So the upfront cost is significant, but from a long-term economics perspective, none of us are rational consumers, which is frustrating from their perspective. So our takeaways from this residential study is that a lot of these efficiency measures, focusing just on efficiency, which is different from conservation. Conservation requires a behavior change. Just focusing on efficiency and doing the same thing we've always done, we can save money over the life of an appliance and a fixture, and we can save a significant amount of energy and water at the residential scale. Water efficiency is a cost-effective approach to energy efficiency and vice versa. We saw that at the city scale, and we also see that at the distributed residential scale. We also did some investigating into rebates and incentives, and there's some interesting examples nationwide of rebates that start to touch on these connections, where there was a natural gas utility that was offering free low-flow shower heads to its customers. They save water, but they also save heated water that's heated with natural gas. So there's a reduced strain on the resource they're focused on, which is natural gas. Yeah.
There was also some like state level policies, right, that mandated shower heads. California had that. I know people
Yes.
were, like, a lot of people were very unhappy with it because they didn't think the pressure wasn't that good. It was a while ago. I don't know when there's like a stick as opposed to a carrot, it's something different.
So from the federal level, there's also been the stick when it comes to fixtures on new construction. So I think it was the Energy Policy Act of 2005 recognized some of these connections and said in new construction, you can no longer put in that 7-gallon per flush toilet. You have to have the 1.6 gallon per flush toilet from here on. That doesn't apply to old construction though, so that's a place for retrofitting. But yes, there's both. This is the rebate would be the carrot approach. There's also a fair amount of evidence of the stick approach that we'll just require it over time, and we'll tell you can't buy any of those incandescent light bulbs anymore, sort of thing. Yeah, good question. So what does all this mean? Really, our key takeaway, which I know frustrates a lot of my students sometimes, they want some earth-shattering discovery, but a lot of times we have to focus on what are the clear key takeaways. And the truth is, if we want to manage any of these resources, whatever your resource of concern is, whether it's green space in cities or water or energy or risk or finances or any of that, managing starts with measuring. And in our effort to try and understand the urban water cycle, we weren't really measuring a whole lot to begin with, so it's hard to manage something if we don't invest in measuring it. So, what's next for all of this stuff? Well, one key hot off the press takeaway is we, as of last Saturday, now have an accepted publication on these water and wastewater utility data, and we have created an open access, freely available database of all of our urban water and wastewater data. Organized everything by city, posted it online using Quasi's HydroShare platform. All of it is freely available for anyone, anywhere to use in an effort to promote these ideas of open data and data sharing. We're also trying to focus more on the residential and commercial side of things and start to understand how do people really use water in their homes with some smart water metering. So we want to start to quantify end uses, to link water and energy consumption inside the building itself, and to start to characterize behavioral effects. People usually laugh at me as an engineer that I do all of these smart water metering things, and I want to understand human behavior, but I don't actually want to interact with the humans at all. Because, as many of you who do social science things realize, there's a lot of bias that comes into asking humans anything. And when you ask humans, how do you use water, they're probably going to fudge those numbers. So I want the numbers to talk to me. I don't want the humans to talk to me, which sounds so very textbook engineer, but that's where we're going. So just to give you some perspective on what this looks like, we've currently got a water meter installed on a home, and we're taking 1 second resolution data. Most water meters are read once a month, if we're lucky. So now, instead of once a month, we're looking every second, and we can start to see signatures of different things. So a bathroom sink looks something like so. I know it's hard to read this vertical axis, but it's flow. I wanted to get everyone side by side, and they're all on the same scale. So this is flow, and our bathroom faucet is a fairly low flow rate. The shower is interesting. This blip right here is when you turn on the bathtub part of the shower before the valve for the shower is opened. So this is technically the bathtub flow, and this is the shower flow, which is right around 2.5 gallons per minute, which is what shower heads are rated at these days. And our toilet also has a similar flow rate to it, but a much different duration in length. And this is a super short shower. This would be a 2-minute shower. So what we're doing, these are each thing in isolation, but in reality, we as humans run a lot of things at the same time. So we might have flushed the toilet, then turned on the bathroom sink to get a drink of water, all while the shower is heating up. And if we combine all of this, we'd see this blue line. And we're working on machine learning algorithms to get us from the right-hand side, all of these things together in a messy format, to the left-hand side, where we can figure out what is happening inside the building envelope with the humans. So key takeaways from all of this is that water and energy both matter. When it comes to sustainability, I'm kind of preaching to the choir because you all do interdisciplinary stuff, but you're probably bumping up against a lot of the challenges that we all have in interdisciplinary work, where it's hard to have conversations across disciplinary boundaries. And a lot of times, naturally so, we all think that our respective area of expertise is the most important thing in the world. So clearly water is the most important thing from my perspective, but energy is also really important. And these are really interchangeable, such that one is an efficiency route towards the other. So with that, I'll thank our sponsors. The National Science Foundation Graduate Research Fellowship funded my student who did all of this data collection effort, and the Siebel Energy Institute has funded a lot of our residential energy and water collection stuff. These are our publications. You probably don't want to write all of that down, so I'll just give you our website here. It's freshly updated because it's time for my biannual website update. So if you would like access to the new publication on water and wastewater utilities, that's on the website, and also a link to the publicly available database with all of those data and any of our other publications. So with that, I will take questions if we have time for questions. Yeah? Okay. Yeah.
Quick clarifying question. Mckenzie Curve is named after a person, or
the company, the consulting firm, Mckenzie & Company. They kind of, I don't know if commercialized is the right word, but they popularized this cost abatement approach when it comes to carbon emissions for the macro economy.
So what's the support of those numbers? In the first half of the presentation, you did a really good job in convincing us that there are no regional trends. There's a lot of heterogeneity in use, consumption, and maybe above all reporting. And at the end, we saw everything aggregated together of don't buy energy efficient this, but do buy energy efficient that. So how much weight can I put into those Mckenzie curves?
That's a really good question, and in that same publication, we tried to get down to regional differences. So we made separate cost abatement curves for New York, LA, and Chicago based on their water prices, their energy prices, and the consumption of outdoor water at those locations. What we found is that nothing changes from cost negative to cost positive, and only a handful of times does the order switch. Good question, though. But that's not representative of everywhere, right? The urban environment and the rural environment are very different, and we didn't have data for rural environments. You had a question?
Yes. Also talking about the abatement curves. I'm curious, are you aware of anyone looking at the differences between home ownership and home and renters markets in terms of, it seems like while the appliance might work the same, the reward and upfront investments diverge sharply.
That's a really good point. So the difference between home ownership and renting or leasing of a home or of an apartment is kind of a tricky thing, because sometimes, at least when I poll my students in Champaign-Urbana, some of them don't even pay for water because their landlord pays it all. Or it's this tragedy of the commons where there's one water meter for the whole building and the landlord divides it by how many occupants there are. And so we all pay everyone's water, sort of thing. I have not done any work in that area, but I do know a team at MIT that, at least in the launch of the Siebel Energy Institute, had gotten seed funding to study that very phenomenon when it came to energy on renting apartments. So they were working on, I think it was an app, a cell phone app that would give as much information, so in an economics market sense, perfect information about how much energy each apartment consumed on average, in an effort to see if people chose more energy efficient apartments in the same general location. I don't know the outcomes of that, but that's where I would start to look for answers. Yeah.
I noticed in the first map of water use that Atlanta was missing. Do you have, so I know Atlanta is like currently being litigated, Tri-State Water Board.
Uh-huh.
They're probably in the 45% leakage range because of the old.
Probably.
Water, wastewater, and water. They're also combined sewer.
Yep. Yep.
What did they tell you when since they're legally obligated to share this data with you?
They didn't.
They just didn't respond.
They didn't. That was one of, in the effort to collect data, my student Chris got really excited when he got data from large cities, and he banged his head against the wall when it came to Atlanta for a long time. He defined what he thought was the right person, and then he'd get kind of sent around to different people to get numbers, and he never did get numbers out of Atlanta. It was a pretty big day when he got numbers out of New York City. But Atlanta is one of those big ones that I would love to know what's going on there with the failed privatization of infrastructure and all of the recent history of Atlanta's water and wastewater systems, but we were not able to get numbers out of them. Yes, legally they're supposed to respond, but we don't really have the money to hire lawyers, that doesn't make friends. We're hoping that by publishing the database and showing here's what everyone else has done and here's all the people who responded to our requests, there's nothing here that's sensitive information, people will be more likely to share data in the future. Other questions? Yeah, me.
So there's a lot of heterogeneity spatially, but did you look at maybe city age or city size as driving the variation?
So one of the things that we're trying to figure out now is what drives these differences in water use patterns, because per capita water is kind of a tricky measure if there's a lot of commercial entities, but in the end it's kind of the best measure we have, and even that is kind of across the board. So we're looking at things like social indicators, demographic information, but also some infrastructure indicators, how many miles of pipe, what's the relative vintage of that pipe. That information is kind of hard to find. We can approximate miles of pipe with miles of roads because a lot of times pipes are underneath the roads. but the age of the infrastructure is typically would correlate with things like non-revenue water percentages, and we're trying to figure out some clear conclusions that come from that.
In terms of broader impacts, have you thought about working with or writing in spaces where people like at American Rivers, right, think about the environmental conservation of water and the environment more broadly and the impacts related to hydrology, hydrological systems on biodiversity, et cetera? The point that you made earlier about water loss also meaning energy loss would be a pretty significant argument for municipality, for folks like American Rivers advocacy groups to municipalities and even county governments, right?
Right.
Have you thought about that kind of outreach?
We've thought about outreach to that extent, especially when it comes to engaging water managers. So right now we're working on a new collaboration with the U.S. Geological Survey on trying to understand what's the important information. So when it comes to feeding information to decision makers, you kind of have to be able to speak their language and to phrase things in a way that makes sense for what problems they're trying to solve. And so we've done a bit of work there in trying to engage water managers. We started locally because we're the flagship university in Illinois, and we're also housed on the same campus as the Illinois State Water Survey, who does a lot of the collecting of data for Illinois water utilities. So that's where we've started, and my sense is that's an art in itself, and there are a whole bunch of lessons to be learned just from that engagement.
Yeah, I think that's some of the work I've seen in other arenas is that having that, like American Rivers or that group is team that's used to talking to science. Many of them are scientifically trained,
right,
but are in the advocacy realm, already know how to do that. And so it's called boundary chains. There's a lingo to it.
Interesting.
Boundary chains between academic research and decision makers.
Cool. I had heard that middle person, middle man, middle woman referred to as a knowledge broker in the literature.
We're looking at that regional heterogeneity. Were you looking at like what is the city's source of water, like where is it coming from, and also like what are local policies that are tied to this use of water?
That's a really good question, and as a next step, that's kind of where we're headed. When it came to collecting data, the challenge is finding the right person and then not asking for too much, but getting something useful. So that's why we started with just flow and energy. Our next steps are along those lines of what's the water source, or what's the portfolio of water sources. For some cities like Chicago, there's one source, like Michigan. There's some cities like Los Angeles, there's several sources of water. And what that means in a resiliency perspective moving forward is the same question but different answers in different cities based on what their inherent priorities are. So it's kind of a next step where we can go with this work. But in retrospect, it's something we probably should have asked, but I'm sure you all have also gotten that email that asks you for 5 things, and if it had only asked for 2, then maybe you would do it right now. But it asked for 5, and I'm going to put it off. Yeah.
So this bit maybe is a little bit more on the economic side, but 2 bits. One is what percentage of water coming from these utilities is going to residents as opposed to commercial use, and then given your abatement code, do you think you'd expect to see a similar thing if you looked at this for small and medium-sized businesses? Are they also leaving a lot of money on the table? You'd expect with a profit motive there, people might have identified or know more of these opportunities and dealt with them compared to homeowners, but I'm not sure.
I'm not sure either. So to your first question, we looked at drinking water coming out of a drinking water treatment plant, not necessarily where it went. So we don't have a split between commercial and residential, except in cities that publicize that information in like end of year annual reports and things like that. What would the cost abatement curve look like for commercial? My sense is that it probably they've probably already invested in a lot of the upgrades that make sense. That said, I think it would be different for like small industry, commercial, light industry versus something like the hotel sector. That'd be the behavior of customers is very different in those senses. When you go to Home Depot and use the toilet, you're probably just going to flush it once, maybe twice. In hotels, there's a whole bunch of literature on water efficiency and behavior in hotels, but the main conclusion is that we waste a lot more water when we're not paying for it. Same with energy. When we're not paying for it, we'll totally crank the thermostat one way or the other. So the behavior that happens in the hotel sector and in large tourism-based sectors is very different, and there's only so much you can do with efficiency versus behavioral change. That'd be an interesting perspective, though. Yeah.
Another variable that I'm thinking about in terms of that might help to also explain the variation of use per capita, was it? Is urban sprawl. And, especially since so much seems to be used for outdoor, there's a big difference in terms of like a brownstone in New York versus a single family home in Phoenix or something like that.
Right,
so I wonder
right.
if that's like, there's a way to, account for that in that analysis.
That's among the social indicators that we're working on trying to tease out right now. In addition to things like miles of pipe, it's urban density and the buildings in that urban core, also the occupants in those buildings. Are we talking about a crumbling inner city that is a lot of vacant buildings, or are we talking about some dense movement of folks into an urban core? Every city's different. I mean, Detroit is not the same as Phoenix, it's not the same as Dallas, it's not the same as Austin.
Anything else? Well, thank you for coming.
Sure.
And Ashlynn will be here for a little bit this afternoon if anybody who didn't sign up to meet.